Hello, this paper is titled Mastering Diverse Control Tasks Through World Models, and it was published in Nature in 2025, and the model is called DreamerV3 or the Dreamer's third generation of Dreamer. Okay. Um, the problem this paper is aimed to address is that most reinforcement learning algorithm requires task-specific tuning. It attempts to solve this by learning a world model and discrete latent state transition. And they demonstrate the ability to generalize it across over more than 150 diverse tasks with a single algorithm without fine-tuning. The model was tested on benchmarks such as Minecraft and Atari. In the case of Minecraft, it was able to solve the task of finding diamonds using only sparse reward without any human data or curriculum. Dreamer is previously introduced concept. The common idea is that it is a model-based reinforcement learning algorithm. It optimizes the polish based on predictions of the future made by the world model. Uh, in Dreamer V1, introduced imagination-based policy learning using a learned world model, and, and use the continuous latent state, but suffered from limited expressiveness and unstable training. And it worked well on simple environments like the mind control should. And and the next year, the Dreamer V2 presented. In Dreamer V2 improved latent expressiveness by introducing discrete latent variables and enabled better modeling of complex environments such as Atari and Moscow, but still required task-specific tuning and was not fully robust across tasks. And finally, in Dreamer VC, achieved the generalization across more than 150 tasks with a single set of hyperparameters. It combined discrete latents with KL balancing and stronger regularization, and demonstrate world model-based reinforcement learning as a practical and stable approach. Let me clarify a few potentially confusing points first. The goal of this paper is not to solve a specific problem like training Minecraft agent. Rather, it is about proposing a reinforcement learning algorithm similar in the street to PPO. The key contribution of this work lies in its ability to generalize. Also, while the paper mentions learning a world model, it does not learn the entire environment directly. Instead, it learns the reward function, the latent representation of the world state, and the transitions between these states. Lastly, although the paper demonstrates learning across more than 150 tasks, this does not mean the model learns all tasks at once. Rather, it means that a single algorithm with fixed hyperparameters can be applied to a wide range of tasks. The reward function and state representation still need to be manually designed. Um, After this is the architecture overview. It is quite simple. Once the world model or the recurrent state space model learned, the actor critic is trained using imagination rollouts generated by this world model. And the rollout refers to a sequential trajectory of state, action, and reward, and next state. This tuples trajectory. The world model consists of a sequence model encoder, dynamic predictor, reward predictor, continue predictor, and decoder. I will explain each of these components one by one. The sequence model is a GRU-based recurrent neural network. It is responsible for running the recurrent state by predicting the current step's recurrent state. Using the previous step's recurrent state, the discrete state, and the actions. The encoder is responsible for converting the input into a discrete state. It also makes use of the recurrent state. If the input data is an image, CNN is used, and if it is a low-dimensional vector, MLP is used. The dynamic predictor, like the encoder, is models that predict the discrete state. However, unlike the encoder, it does not use the sensory input, just the recurrent state. This is because when training the actor critic using the round world model, the actual environment is not observed. Therefore, a model is needed that can predict the discrete state using only the recurrent state from the sequence model. The reward predictor is a model that predicts the output of a predefined reward function. When training the actor critic, the actual reward function is not used. Instead, the agent learns from the output of the reward predictor. The continue predictor is a model that predicts whether to proceed to the next step or terminate. This model is necessary because when training the actor critic using the round world model, continuing rollout beyond the terminated state could lead to serious problems. The decoder is a model that takes the discrete state and the recurrent state as input and predicts the sensory input. It is not required for training the actor critic, but it is necessary for learning the discrete state representation. And this is loss part. The loss used to train the world model can be broadly divided into three components: the prediction loss, dynamic loss, representation loss. And first, the prediction loss is related to the decoder and reward predictor and continue predictor. And the next two losses, dynamic loss and representation loss, are similar but deeper in their gradient flow. So the order is important. In the equations, the SG operator stands for the stop gradient operator. In the dynamic loss, gradients from the encoder are blocked, so only the dynamic predictor is updated. As it described earlier, the encoder and dynamic predictor have similar structures, differing mainly in whether they use sensory input. Given this, the dynamic predictor is expected to match the distribution produced by the encoder. However, since both the encoder and the dynamic predictors are trained simultaneously, it is important that the encoder's optimization does not diverge too far from that of the dynamic predictor. To address this, KL balancing is used. Both the dynamic loss and the representation loss are applied to minimize the difference between the two distributions, but the dynamic loss is weighted 10 times more heavily. Additionally, a technique called free bits is used. This prevents the dynamic loss and representation loss from becoming too small. While it may seem desirable for these losses to be low, this is not always the case here. In sparse reward settings, the model might compress everything except the parts needed to predict the reward, discarding other useful information. This leads to what is called representation collapse, a situation where latent information disappears because minimizing the loss encourages discarding parts of the state that don't directly affect the reward. In the representation loss, unlike in the dynamic loss, the gradient of the dynamic predictor are blocked. This causes the encoder to slightly adjust its distribution to align with that of the dynamic predictor. Now, with the trained world model, the actor critic can be trained. Unlike traditional model-free actor critic method, this approach does not involve simulation with the real environments, which allow for much faster learning. However, this might raise the following concern. Wouldn't it be highly unstable if no actual simulation is performed? But the imagination is performed in discrete latent state space, not at the pixel level. This helps remove high-frequency noise, making the predictions more abstract and stable. Also, the loral length is relatively short. It is around 15 steps. And moreover, the actor critic is robust to the prediction uncertainty in rollouts. As long as the overall trend is correct, it performs well even with some noise. Additionally, since the reward is predicted by the world model itself, there is an opportunity to reduce bias. The perform, they perform an extensive empirical study across 8 domains that include continuous and discrete reactions, visual and low-dimensional inputs, dense and sparse reward, different reward scales, and 2-dimensional and 3-dimensional words, and produce procedural generation. Dreamer matches or exceeds the best experts, whether they are model-based or model-free. In the domains, they are applicable to an outperform PPU across all domains. It is an additional page. It was the question of my question before understand this paper. About the question, only image inputs, and it is not limited to image input. Experiments were also conducted in domains with low-dimensional vector inputs, and this was what I had been curious about too. Does it deserve to be published in Nature? And about this question, unlike model-free methods like PPU or DQN, which require task-specific tuning to perform well, DreamerV3 shows consistent performance without any tuning. Moreover, in a challenging environment like Minecraft with long-term goals, sparse reward, and difficult exploration, it succeeds in collecting diamonds without using human data, curricula, or task-specific engineering. This was considered a research milestone. This is not just a theoretical possibility, it represents a general reproducible solution that actually works. DreamerV3 achieves high performance without a complex structure and has been recognized for its maturity as a general purpose algorithm that anyone can use. Thanks.